Hello everybody and welcome to Lesson 3 in Chapter 1 of Damage Control Assistant Senior Enlisted Curriculum with myself, Lieutenant Timothy Mueller. I'll be the instructor on this lesson, which is about the writing arm and writing moment. And I'm going to bring a diagram that we had seen a lot in Chapter 0 back. And I'm going to take a look at what we've already seen in the last video when we talked about moment couples. And let's kind of start bringing ship stability into the entire picture. So you've seen this diagram before. This is just any vessel, just a generic ship's hull that's underway steaming, nothing crazy going on here. We have a waterline, that's right here, waterline 0. We have a center of buoyancy, that's directly along the center line of the ship, as well as center of gravity, that's directly along the center line of the ship. We've already learned that the magnitude of gravity, the force of gravity down, is equal to the magnitude of the buoyant force that's acting up on the hull. So the force of gravity is acting through the center of gravity, and that force of gravity is equal and opposite to the force of buoyancy, which is acting through the center of buoyancy. Now let's take this vessel and let's incline it over some small angle of inclination. So let's say 5 degrees. So we have this scenario, and this is just drawn 2 different ways. And you'll remember this from Chapter 0. Here, we're looking at it in respect to the waterline. So the waterline stays constant, and the ship just rotates about the waterline. In this, more of an inertial frame, we have the ship staying still, and then the waterline rotating about that ship. Okay. So let's go number 1 right here. We know the center of buoyancy is going to swing through an arc at small angles typically being the range from 0 to 7, some hulls being 0 to 10, but typically we'll say 0 to 7 to stay safe. Okay. We know that B is going to swing out, but the center of gravity, assuming that no cargo shifts or anything strange happens with the vessel, is going to stay the same. So the center of gravity stays the same, force of gravity still acts through the center of gravity. Center of buoyancy swings over. Force of buoyancy always acts up through the center of buoyancy. So now we have the 2 arrows, same magnitude as we had before, but they're not directly opposing each other. There's a distance in between them. What is this distance, though? We call this, in naval architecture, the writing arm. And I had looked at it, I had hinted at it in the previous video. However, now we're going to actually put a name to it. And we call this GZ, the writing arm. Z being a point along that force of buoyancy that is directly perpendicular to where point G is. So if we take point G and we look at the whole line of buoyancy, if we draw the shortest possible distance from that point G to that line of B, the perpendicular distance, that is going to be GZ, or, as you can see over here, the writing arm. Now let's go into the inertial frame. We had talked about, in previous videos, how we lose buoyancy on one side and we gain it on the other side, and that is what causes the center of buoyancy to shift over and up, swinging through that arc. If we keep this frame inertial like this, we are going from this waterline here, so this shape and this wedge here being submerged. Now when we move that waterline to waterline 1, this triangle here, this wedge, is no longer submerged, and this here is submerged. So we have this shape, which is always submerged, and then this wedge, which is submerged, bringing that center of buoyancy over. However, as we're looking at this, gravity is not acting straight up and down anymore. Neither is buoyancy straight up and down. It always acts with the waterline. So I use this inertial frame just to show you how this wedge is moving over and up, moving the center of buoyancy. However, if you were to actually use this to model ship stability, you would have the lines of gravity and buoyancy always shifting at different angles. Because remember, even though this is physically correct, this isn't exactly what's going on. This is what's going on. So we want to keep G and Z as close to what we observe in nature, which is just straight up and down, as possible. However, in this model, if we were to try to find the righting arm here, we would go from G, the perpendicular distance, straight to the line of buoyancy, which would be right here. So this would be the point Z, and this would be our righting arm, not this, which is how far that center of buoyancy moved over. So remember, it is the perpendicular distance from the point G to the line of force of buoyancy. If you're thinking of keeping the ship constant and moving the waterline, remember that as you move that waterline, the direction of gravity and buoyancy shift as well. So it might be a little bit more difficult to actually consistently use this model. So it's probably better to just use this right here and always think, okay, gravity and buoyancy is straight up and down, so I want to go across. Whatever that across distance is, that's going to be my righting arm. I talked about moment couples, and we know that a moment couple is just two equal forces, so we have gravity and buoyancy, acting in parallel lines in opposite directions. Parallel lines, opposite directions. So we have a moment couple. And we saw in the last video, no matter where we take that reference point to be, the moment couple that we get is always going to be the same. So instead of taking a moment couple about this point that's right in the middle of the righting arm, how about we just look at like we did with point alpha in that last video. Let's just take this point G. Now let's take the moment couple about point G. Okay, so we know that gravity, no matter what its magnitude is, it's always going to be zero because it's acting directly through the center of gravity. So there's no distance from that point. Buoyancy, however, has a distance, which is the righting arm, and it has a magnitude. That's the displacement, which is going to give us the righting moment, the couple, the moment couple, is going to be GZ times delta, or the righting arm times the displacement. All right, that was a really quick video on the righting arm and righting moment. I've already gone into this and kind of hinted at what the righting arm and righting moment was in previous videos, so I didn't dive into it too much right here. However, it's a very basic term that we need to know in order to start introducing more complex terms like the stability triangle. If you were the DCA or the engineer officer on a boat and the captain wanted to know how stable the ship was, you could tell him, at 10 degrees, we have a righting arm of 3 feet, or you could say we have a righting moment of 20,000 foot long tons, but that isn't really going to tell him or her anything. You really can't get a grasp of how stable a ship is just based on righting arm and righting moment. You can compare different conditions that a ship is in based on the righting moment and righting arm and say, okay, we're a little bit better here than we are in this other condition because we have a better righting moment at 7 degrees. However, it doesn't give you an overall picture of the initial stability of the ship. In the next lesson, we're going to talk about the stability triangle. We're going to get back into the meta center that I talked about in chapter 0. And now we're actually going to start seeing initial stability in all of its glory. Until then, I'm Lieutenant Timothy Mueller, and I hope you have a great day.